For the last presentations of the seminar today, I would like to invite Engineer Fawad Najam, AIT PhD candidate and co-author of the cross-structure book, together with Dr. Naveed Anwar, to deliver a presentation on a modified response spectrum analysis procedure for tall building. Engineer Fawad, please.
As the last speaker for today, I know that I have to be very clear and simple and good to get your full attention. So I will be. The topic for my presentation may seem strange to some people because the response spectrum analysis, as we know, essentially is a linear static procedure with some dynamic considerations. So how can it be used to determine nonlinear demands of tall buildings? In order to get answer for this question, you have to listen to my story. So simple, clear, just lean back and listen to my story. I would like to start where Dr. Naveed left yesterday about the use of mode shapes in understanding the dynamic behavior of buildings. The idea that the random vibration of an oscillating structure can be described, can be seen, or can be decomposed into some regular, simple, harmonic motions, mode shapes, has profound applications in seismic analysis of structures. This idea is so simple, elegant, and conceptually so appealing that it is still we believe that is the core of structural dynamics today. So just to put things in perspective, quickly I will just give you an historical overview of where it all started. Soon after the invention of calculus, as also mentioned by Dr. Naveed yesterday, the governing differential equation of motion for moving objects and their solution were started, and D'Alembert was one of the first persons who considered the dynamic equilibrium of moving objects, and he came up with a solution involving wave equations. And soon after him there was a giant Lagrange who for the first time tried to understand the random vibrations of vibrating strings of a musical instrument like guitar. And he concluded what is now the cornerstone of structural dynamics now. He concluded that the random vibrations of the strings of a musical instrument can be seen as a superposition of few simple waves, and the number of waves can be theoretically equal to the number of particles which are making that string. And he called them at that time characteristic functions. Now we call them mode shapes. And after him was another giant, Lord Rayleigh, who published a book on acoustic theory, the theory of sound, in which he first time explicitly explained the idea of modal superposition. This important book is considered one of the breakthroughs in structural dynamics, and interestingly, it is not well related to structural dynamics. In 1908, quickly following the history, there was a big earthquake in southern Italy in 1908, and soon after that, the scientific community in Italy started different events and different attempts to somehow revise the way we think of our structure and the way we design them. As part of their preparations or as part of their improvements in seismic design, they held a competition, in fact 2 competitions, about new ways of designing structures against earthquakes. And the person who came first in both of those competitions was the fellow on the left of you, Arturo Danuso. He for the first time proposed the idea that if we can take the idea of modal superposition from acoustic theory and apply it to the random vibrations caused by an earthquake, we can simplify the response and we can understand it better. He was also the first to derive the governing differential equations for single degree of freedom system as well as for 2 degree of freedom system. The first mathematical formulation of response spectrum analysis appeared in a PhD thesis of Belgian-American aeronautical engineer. The guy on the right of you, his name was Fawad. He was under the supervision of another well-noted mathematician, Theodor von Karman, who has a lot of contributions in signal processing also. So the standard response spectrum analysis procedure, as we know it from different codes and standards, these two professors have a lot of contribution in its current form. Professor Ray Clough as well as Professor Edward Wilson. Someone from our guests have mentioned a personal note from Edward Wilson recently is being circulated and gone viral almost about the termination of response spectrum analysis. He kind of disowned it and regret its development. I am not in a position to say something about the future of response spectrum analysis, but we feel that the idea of modal superposition is so simple, elegant, that if you take it out from structural dynamics, all you can left is with time history analysis, which is kind of a black box. You don't know what the engine is doing itself. So we feel that the idea of modal superposition will still remain in structural dynamics for some more time, not because that it offers more convenience nowadays compared to time history analysis, because time history analysis is no more an issue nowadays, but because that it provides the response mode by mode. It tells you the constituent of response. From design point of view, the real purpose of structural analysis is not to come up with, as also explained by Dr. Prameen, is not just to come up with the accurate number, but it's also to come up with understanding and with the constituent of behavior. You have a clone of your model in software, and you can kick it in software. You can always play with it, and you can check what makes its response. Analysis is not an ability to simulate the structure in its current form. Analysis is to be able to play with it, to be able to control the response. In order to control response, you need its constituents. For example, we were discussing about the control mechanisms or dampers. How can we design them? How can we check the optimum location of those dampers without having the idea of from where the response is coming, from which mode, what should be the location of a damping mechanism, what frequency it should be tuned to suppress. So this all information is only obtained from if you are able to decompose response and not, the time history number can be more accurate, and it is there always for you to final check for all purposes. But if you really want to get the feel of your structure, if you really want to understand its behavior, we feel that the idea of mode shapes should remain in structural dynamics theory. I will quickly just share one small story with you. My advisor once asked me that, have you ever seen a real simply supported beam as part of a real structure with a real pin at one end and a real roller at the other end? And I replied him that no, because these pin and roller are mere structural idealizations, and the actual support condition is somewhere in between roller and pin and fixed. But he said no, he had seen actual simply supported beams as part of real structures, and he said that I have asked those engineers why they designed like this. I mean, it was so natural or easy for you people to put some fixity on those supports. You could have reduced moments on other components. You could have induced additional redundancy, rendering the structure more safe. But those engineers said something which was kind of awesome. They said that we don't want additional security. We want the confidence on our understanding of that structure. We want to crystal clear, know that this number should be in tension, this number should be in compression. We preferred the understanding over a false sense of additional security in the form of redundancy. So we want the structure to behave simple. And this appreciation of understanding the structural response, this romance of knowing the behavior is something which is not being taught at engineering schools. Continuing further, because this are all the reasons I am telling you that why we should still stick with simple procedures, elegant ideas, and we should always stick to our main concepts. Continuing further, much has been said in last 2 days on the criticism of traditional building codes. So let me just quickly put my share in that also. I was watching one lecture from Professor Jack Maley from Pacific Earthquake Engineering Research Peer, and he showed a quotation from Professor Hardy Cross. That guy, the fellow on your left, is Professor Hardy Cross, the developer of moment distribution method, the method which was mostly used before the prevailing of finite element analysis. All engineers, the practicing engineers from previous generation maybe know it, but it's now kind of an obsolete method. So he has something very interesting to say about standardization. He was a professor of civil engineering in University of Illinois. He said in 1952, as the size and complexity of projects increased, it became desirable and even necessary to set up a series of routine procedures for analysis and design. Well enough, understandable. With these standardized formulas and specifications and methods, it became possible to use a greater number of men and men with less training to produce engineering works. I will not comment on this statement, but you can just see and you can make your opinion based on that. This is Professor Hardy Cross, the inventor of moment distribution method in 1952. He also sees standardization as a check on engineers who don't know anything, and the engineers who know too much and they just want to get away with things, or set up as an intellectual assembly line has served well in the engineering world. So this is just a message about standardization. This is what Professor Hardy Cross, just check the time when most of the standards or codes or building codes, they were in their early stages. So without much commenting on it, but you can see that if you have the insight on all the codes and standards, by their very design, they are in a kind of their intention seems to be producing the men with less training to produce engineering works. Having said that, just quickly review that the standard response spectrum analysis procedure, which is the most prevailing design analysis procedure for buildings. This is in its current form available in ASC 7, IBC, and Eurocode as well. It starts with eigenvalue analysis, modal analysis, and then you can pick the spectral accelerations from a demand spectrum corresponding to each mode, and then you can convert those accelerations into forces, and those forces you can combine them using some suitable modal combination rule. And at the end of that procedure, you are asked to reduce those elastic forces with a response modification factor R and to come up with design forces. The displacements they have to be multiplied with a displacement amplification factor. I think all young engineers will agree with me that we are highly uncomfortable with all these modification factors and load factors, amplification factors, response modification like this. You spend a lot of days to come up with a number, and then code says that you should just divide that number with 5 or 6 or 8 maybe. It's kind of a rough treatment to your hard work which you put in setting up a sophisticated model. And then, so anyways, much has been said about the inadequacy of this R factor, and my presentation is basically about that. It is well established that each vibration mode doesn't experience the same amount of nonlinearity. Many people have tested it, and it is kind of a everyday routine experience of most of the engineers who want to dig deep into modal response of each mode. So there are some solutions which are being proposed in research community basically. The most famous solution for this problem is modified modal superposition. Basically, Presley and his team have proposed this. He simply recommended that this R should only be applied to first mode, because mostly the inelasticity affects the first mode. So only that mode deserves the reduction, and higher mode doesn't deserve that reduction by R. Another approach to cover that thing was shear amplification factors by Eurocodes, and maybe overstrength factor is also there. So some people have tried to use those amplification factors or overstrength factors to come up with a realistic estimate of true demands. There are procedures which recommend that you should use a different R for each mode. For modes which are about to remain elastic, you have to use R equal to 1, means no modification. But in order to get the response modification factor for each mode, you again have to do pushover, and for that pushover you again have to make nonlinear model. So if you have a nonlinear model, why don't you do time history then? Another approach, again from the same group, Presley and his colleagues, that you can modify the modal properties of higher modes to account for their behavior, difference in their behavior with first mode. So our approach in all this is knowing fully that each mode is different. The response from each vibration mode doesn't experience same amount of nonlinearity. We simply try to separate them using an approximate modal decomposition technique. In fact, we have tried more than one techniques, but I will present here one. The basis of all modal separation techniques is this idea, which is the equivalent single degree of freedom system idea. The idea is simple, that you subject your multiple degree of freedom system to lateral forces, monotonically increasing lateral forces, and then you reverse the direction, and you push and pull and push and pull and apply these cycles, and resultantly you will get a hysteretic response or cyclic response, look something like this. If you use the first mode shape pattern to push and pull your structure, this hysteretic response is the first mode response. If you can come up with a model which can actually map this hysteretic response, and that model you assign to a single degree of freedom system, the response of the single degree of freedom system is expected to be similar to that vibration mode of a multiple degree of freedom system. So that's how you can convert one specific mode of vibration of a multiple degree of freedom system to its corresponding equivalent single degree of freedom system. So you do it for enough number of modes, this cyclic pushover, you map them their hysteretic responses and get a corresponding single degree for that mode. If you have a lot of these single degree of freedom systems and you subject each of them to one ground motion and sum their response, it is expected to remain same or equal approximately to the time history analysis of the actual multiple degree of freedom system. So this is the basic idea of modal separation, that we convert each vibration mode of a multiple degree to an equivalent single degree, and we run the ground motion to that, and then we sum them to get the combined response. So the combined response of these lollipops should be equal to the time history results of this multiple degree of freedom system. We have applied this idea to a number of case study buildings in the last 3 or 4 years. I will present just quickly the results of 3 case study buildings which we selected. They are existing buildings in Bangkok as part of a project funded by BMA. The one is 44-story building, and then 33, and the shortest one is a 20-story building. So we separated their modal responses to understand that they experience same amount of nonlinearity or different, or which mode deserves what reduction factor. So after doing it again and again for different buildings, we again reinvent the same thing, that each single degree of freedom system is different. Each will have a different cyclic response, different governing parameters, and everything is different. Just to give you an idea, one example from 44-story case study building. The black line, the thin black line, is the actual cyclic pushover analysis for first, second, third mode of the full multiple degree of freedom system. And the blue line is the response of that mode's equivalent single degree of freedom system. And you can see that if you overlay both of them, the first mode is experiencing some stiffness degradation, some softening, maybe cracking of shear walls or something. But second and third mode response is in the linear elastic range. The blue line is not crossing the yield point or the cracking point. So it again confirms that second and third mode doesn't deserve the same amount of reduction. In fact, it doesn't deserve any reduction at all. So the second and third mode response is kind of quasi-static or elastic response. Only first mode deserves a reduction, and maybe not that much as 5 or 6 or 8. So another example results that if you use that modal separation technique, in which you represent the vibration mode of each multiple degree of freedom system with an equivalent linear, and then subject those equivalent linear systems equivalent single degree of freedom systems into that ground motion and sum them. The red line here shows the summation of first 3 single degree of freedom systems, and the black line is the envelope we get from time history analysis. So and there is a reasonable matching for that in displacement, in drifts, in story shears, as well as in moments. This is a very beautiful picture. It shows that the complex response of that 44-story building can be described by just three modes, 3 single degree of freedom systems, 3 lollipops. You just come up with 3 accurate modal properties, and you can get approximately same response as the time history result of that 44-story building. So, but the beauty of this modal separation is not this, that it gives result equal to time history analysis. This is not its beauty. The beauty is that once you are sure that this response is going to match with time history, you can always see the response mode by mode. First mode, second mode, third mode. You can actually decompose the combined response into modal contributions. And obviously it is kind of a big information that which mode is contributing how much and where along the height of that building. So once you know that this approach, this uncoupled modal response history analysis, this summation of single degrees, the extension of classical modal analysis is working for nonlinear systems as well, you can come up with something like this. The figure on the left is showing the displacement, the combined line is the black line, and then the decomposition of that displacement, where it is coming from. obviously displacement is controlled by first mode, so the maximum contribution is from the first mode. Second and third vibration modes are not contributing much in displacement as well as in drift. But if you go to Story shears, you can see here the contribution of second mode is highest here, but first mode is lower and third is even lower. So if you want to suppress Story shear, you should pay more attention to second mode, and this information you are not going to get from time history analysis. This is important. Modal is controlled by first mode, but second mode is also have some contribution. So you can always decompose response in modal contributions, even in nonlinear range, approximately. Obviously, this approach of modal separation has some inherent assumptions. The vibration modes are not considered, the modal interaction is not considered, the modes are considered uncoupled. But researchers have shown that this coupling effect for lower levels of nonlinearity can be ignored, but this has this assumption as well. So, knowing this thing, that this idea is working, this modal separation thing is working, the complex response of a nonlinear single degree of freedom system, a nonlinear multiple degree of freedom system can be seen as a few nonlinear single degree of freedom systems. We extended this idea to come up with this modified response spectrum analysis method. What we say is that we have a nonlinear structure subjected to a ground motion, and we know that we can approximately decompose it into 3 or 4 or any number of significant vibration modes using this approach which I have explained before. Why not we just extend it and we convert those nonlinear single degree of freedom systems into their equivalent linear counterparts, and we invoke another beautiful idea which is called equivalent linearization, and it is based on the assumption that a modified linear elastic structure can somehow represent a nonlinear structure. The ATC40 capacity spectrum method is based on that. A lot of equivalent linearization methods are based on this idea that a modified linear structure with a delayed time period and with an additional damping, it can mimic the behavior of an actual nonlinear system. So why not we invoke that idea here and we convert those nonlinear modes or single degree of freedom systems into their equivalent linear counterparts. And then once we have this with reasonable accuracy, we just require a linear analysis for that. We no more require nonlinear analysis because these are 3 linear elastic single degree of freedom systems. So we mix these two ideas, the idea of modal separation and equivalent linearization, to come up with this basic concept of modified response spectrum analysis. What we can do is that we can just modify our linear elastic model, and if that modification is smart enough, the response spectrum analysis of that modified method should give results close to time history results following this path. We understand this is a two-fold assumption. This itself is an approximation, and then the vertical this conversion is also an approximation. So it's a double assumption, but still we have tested this idea, and it is shown to work well for real case study buildings. I will show you the results in next few slides. To explain more, we just started from nonlinear time history analysis or response history analysis, and then we decompose it into its modal contributions, uncoupled modal response history analysis, and then this guided us, or this gave us another idea that why not we come up with this modified response spectrum analysis. RSA is widely used procedure in design offices. So if we can have an improvement based on that, based on this improved understanding of modal responses, so why not we should do it? So we proposed this RSA procedure, modified RSA procedure, and we are still developing it. It is still not complete, but during its development it is giving reasonably accurate estimates. So these were some of the solutions I showed before. People have proposed that how can we help response spectrum analysis? How can we improve it? How can we stop it from diminishing among engineering community? But we propose one new approach, that is equivalent linearization, which was not tested before. Just to give you an example, that this period elongation, or when a single degree of freedom system enters into nonlinearity, its period elongates. And just to show that it is a real phenomenon, it's not a conceptual idea. It is a real phenomena. What I did is that I separate the first mode history response of 44-story case study building, which I showed before, and I apply the scale factors to ground motions. And you can see that I zoom that part of the history here. You can see that the wave or the response, displacement response, basically with the least factor have the least time period. It is completing one cycle in the least period. And as I am increasing the scale factor, the amplitude is increasing, but at the same time period is also increasing. So this also gives us a clue that why not we just increase the time period for a single degree and then check whether it is matching with corresponding nonlinear system or not. So this is the basis of that conversion of a nonlinear single degree into an equivalent linear single degree. We have a nonlinear model with a nonlinear forced deformation behavior. What we can do is, I will explain the most simplest idea, because people have tried more ambitious procedures to come up with equivalent linear properties. But the most simple idea is that the secant, the line joining the maximum amplitude of a nonlinear single degree of freedom system, the stiffness corresponding to that maximum amplitude can be used as an equivalent linear stiffness. So a system, you can see here, which has that stiffness, which is the secant stiffness of a nonlinear system, can represent an equivalent linear model. And about damping, we have a classical approach called equal energy assumption. People have tried more accurate and more detailed procedures also, but this dates back to 1930, this idea that why don't we just equate the energy dissipated by a nonlinear system with the energy dissipated by a linear elastic system. So we just equate the area enclosed by a nonlinear forced deformation behavior with the area enclosed by this linear line, equivalent linear line. So when we equate these two areas, we can come out with an additional hysteretic damping. So just add that damping to your equivalent linear system, and it is ready to mimic the behavior of that nonlinear system. So this is the basis of conversion. So we can convert a nonlinear single into an equivalent linear with elongated period and additional damping. We can count more than 50 different analysis procedures, different studies proposing how we can convert this, how can we carry out this conversion efficiently along the last 2 decades. So, but we picked the most simple idea, this one, which was tried initially some 30 years before, and still the most commonly used among the equivalent linearization approaches. And we just put it in our modified response spectrum method. What we did is that we had nonlinear models of our case study buildings, and we conducted their monotonic pushover analysis, and we monitored their stiffness, softening. You can see that you can always check the damage or softening of your structural elements with the increasing lateral load. So point by point conversion of this pushover analysis, pushover curve into because you can monitor the stiffness here, and all along the curve you can check the stiffness, the secant stiffness. So you can just convert the pushover curve into a secant stiffness versus roof drift ratio curve, and secant stiffness can be converted to time period. So you can convert this pushover curve into a delayed time period versus roof drift ratio curve. This is how we treated the period elongation, the most simplest approach of equivalent linearization. For damping, what we did is that we carried out for our case study buildings the actual cyclic pushover analysis, and we calculated the actual area enclosed by each loop, and then we equated it with the triangular area as I showed before, and we came up with the additional damping required for each case study building, for each mode of each case study building. So we came up with these kind of curves, which are showing that, for example, the equivalent period or the elongated period normalized to the initial period versus roof drift ratio of the first mode of this building is this much. So using these curves, which we convert from pushover analysis, both monotonic and cyclic, we can estimate somehow that how much period will be elongated at what roof drift for each mode. And similarly, we can come up with these kind of curves about damping. That if we are given the roof drift ratio, we can estimate that how much is the additional hysteretic damping we require for each mode. So if we can estimate these two parameters for each mode of each case study building, we can simply apply modified response spectrum method, because we can devise ways that how can we smartly elongate the period of our model. We did this procedure, by the way, for 3 case study buildings as I showed before, and these were the results we got for 20-story, for 44, for 30. The trend shows that we may come up with a general curve for period elongation, and this is our ultimate target. We want to present this modified response spectrum analysis as an improved design procedure and not as an improved performance-based analysis procedure, because it is still a linear static procedure based on modal superposition. So it has all those limitations. What we can do is that we can modify our linear model and we can get rid of that R factor. So this period elongation and additional damping will give us just enough reduction for each mode which is required to match with nonlinear time history analysis. So without having a nonlinear model, we believe that you can still get closer to it with a modified linear elastic model. Sorry for that. Okay, so I will just quickly tell you the analysis results we got. We tested this idea for these 3 case study buildings and for these 3 sets of ground motions. We wanted to check the idea for different types of ground motions. So what we did is that we selected one set which was matching this set 1 was matching with the uniform hazard spectrum for Bangkok, and then one set we got for the short period ground motions, the typical ones from shallow crystal earthquakes, and one set we got for very long period ground motion which has high spectral acceleration in long period range, the time period more than 3 seconds. So if our idea is working for these 3 different types of ground motions, we can continue further for further investigation, and these are the results we got. The black line in this, all 3 modal responses of Storey shears of one of the case study buildings, mode 1, mode 2 and mode 3. The black line in that shows the response from the appropriately mapped single degree of freedom system mapped to the cyclic response of that mode. It means UMRHA. So this is considered to be the benchmark of accuracy. The decomposed response from NLRHA is the black line. So if our analysis results are matching with the black line, they are accurate. If they are not accurate. This is our benchmark. So you can see that the green line, which is our modified response spectrum analysis from a linear elastic model having a delayed period and additional damping, is matching beautifully with UMRHA results, while the standard response spectrum analysis, which recommends to reduce each mode by same response modification factor, that is 4.5 in this case, is underestimating significantly. For first mode, maybe the error is okay, but second and third mode surely don't deserve that reduction as prescribed by standard RSA. But our modified response spectrum analysis is able to capture that effect for one ground motion set. Quickly I will show for another ground motion set similar kind of observation, but okay, this is not that much hopeful, but still better than the standard RSA. And for third ground motion set, again we have this beautiful match from our method with time history analysis. Not time history, basically the decomposed form of time history, UMRH. Combined response, if you see for one ground motion set for UHS for Bangkok, you can see that the performance of standard RSA for displacement and inter-story diff ratios is a bit okay, but look at the forces. The red line, which is standard RSA, is significantly underestimating, and we all know that why it is. It is because of the reduction of second and third mode also, which actually remained elastic, but since code is saying you should reduce them with R is equal to 4.5. For third ground motion sets, again same picture. Our modified response spectrum method is in inter-story diff ratio may not work well in this case, but overall, if you have a competition with a method which is wrong by a factor of 2 or 3, you can have these kind of things and you can further tune it and come up with more improved ideas. For third ground motion set, again the green line is more close to black line compared to the standard RSA, the red line. Local response is a kind of a challenge because obviously we have to delay the structure's time period, and the local response is sensitive to how we delay that time period. One way was to apply the stiffness modifier just like ACA 318 recommendation to throughout the building structural members which are expected to crack. And we first tried this idea, and then we are still in a process of getting a more smart conversion which can help us in getting more accurate estimations of local response as well. But with this just direct application of stiffness modifiers, you just see the results. That this standard response spectrum method, this red line, is significantly underestimating the moments in columns. Even with a multiplication of overstrength factor of 2.5, the dotted line is still not capturing the dynamic amplification. And by the way, our modified response spectrum method is also not that accurate in capturing the dynamic application because being based on modal superposition idea, but still it is better than this current practice which everyone is following in field. About shear and shear wall and moment and shear wall, again the same picture, that our procedure is providing relatively better results than standard RSA, and even with the application of overstrength factor, which is not accounted for in this case. So I will just end up with this, because I cannot boast too much about MRSA, because we still are facing the same limitations which are attributed only to a method which is based on modal superposition idea. So, that one should be negatives of MRSA, both cannot be positives. Sorry for that mistake. So, the negatives of MRSA is that it is a linear static procedure. So, all of the criticism which standard response spectrum analysis receives, this procedure will also receive. Except that we have found out response modification approach which is more realistic, which can relate the modification amount to the actual nonlinear state of the structure. So no more R factor, we can just case by case, mode by mode, modify the results. Modal combination rule is still a challenge. People argue that SRSS is not an accurate modal combination rule, and this limitation is still there with our MRSA, and accuracy of local response is also an issue. But positives are that it is conceptually superior. It is based on more understanding, not just the direct scaling down of ground motion. It is based on the idea that each mode should be treated differently. So it is conceptually superior compared to the current prevailing code-based RSA, and it is simple, provides mode-by-mode response. As I said, that modal response is the basis. The black box is not the solution sometimes, and doesn't require nonlinear modeling. This is one of the positive things, that even if we are not able to capture some of the accuracies which are expected we should capture, but look at the impact this idea can have on practice. That if you give a designer that accurate curve of period elongation and additional damping, without knowing nonlinear modeling, he can still get results which are close to nonlinear time history analysis. So, summary, just last slide, that this is a kind of a flow for our proposed procedure. Instead of now the spectral acceleration spectra, we have a displacement spectra now, and we have these curves which I mentioned, which relate period elongation with the state of the structure. In this case, it is roof drift ratio, and we have the curve which can relate the state of the structure with additional damping required. And if we can accurately predict the additional damping and period elongation, we can come up with a smart model which can mimic the behavior of a nonlinear model. So the summary is that with a clever modification of a linear elastic model, say made in ETABS, can give you results which are only expected to have from a nonlinear model, say made in Perform 3D. And by the way, I am not saying that you should not learn Perform 3D. I'll stop here. Thank you.
Thank you very much, Engineer Fawad. He's going to be so famous after the million copies of book sellings. And we have come to the end of the seminar today, and at this occasion I would like to invite Dr. Nabil Anwar for the closing remarks.
Thank you. Well, first of all, I would like to thank all the participants for being with us for 3 days. It's not easy. If I was you, I would run away after maybe first half and go and have coffee somewhere. So I really congratulate you for sticking with us, because some of the presentations are quite heavy. We tried to mix them up. We invited some architects with interesting stories. We also tried to show some videos to keep your interest. But as I promised, and as I mentioned, that things will get serious today, and they did get serious today. And I can see people are getting tired. It's the third day, and also the topics are getting more heavy. But the fact of the matter is that this is a difficult task, what we are trying to talk about. It is more refined. It is more, I would say, gives you a better understanding of what's going on. And obviously, one thing that we all learned from this experience, and everybody talked about it, that we still have difficulties with the building codes in terms of their application when it comes to earthquake, when it comes to large loading, when it comes to estimation of the response, and so on, and their descriptive positions. And please do not get us wrong. It doesn't mean that you go back and 2-story building or a small building, you will also start to challenge everything. The codes have their very clear purpose, and they are still applicable in many of the cases. There are just few issues with the codes that we have tried to raise. But when it comes to all building, then it becomes serious. Because as you can see, many of the questions that we raised, even last presentation by Fawad and other things, is all related to higher mode effects. So if the buildings are still controlled by the first mode, then these issues do not become that significant. Because first mode, it seems that the codes are getting more or less in the right direction. So the building is not too high. If the building is within the code specified parameters, the code should give a reasonable, respectable numbers in most cases. Just to conclude the whole seminar, especially today, I think the first day we talked about some new developments. We tried to see where the future is going in terms of the resilient space design, in terms of the risk-based design. We also look at how the methods are changing, how the tools are changing. Now we looked at a modified response spectrum method that might be something that's an alternative. And obviously, I mean, we can see that not everybody is going to do nonlinear analysis. It's just impossible for every structure, not very soon anyway. So there is always going to be need for other refined methods that people will use. And as a quick design, as an alternate design, as a design where the certain limits are justified, then we will use those methods. So just like pushover, where it started, it was almost similar, the same problem. They ignored dynamics, and they said pushover is very good, it has nonlinearity, but then people found that it doesn't work for higher modes. Then modified pushover methods came, 25, 30 modified pushover methods came into being through research at that time, and then most of them gradually also getting out of fashion. Similarly, the modified response spectrum method definitely will come, more will come, but ultimately, I don't know where the practice will end. But what we know that people are trying to understand more. All of this is trying to understand more about how the structures behave, how we can design them better, how we can detail them better, how we can make them safer, how we can do it quickly, how we can do it economically. So it's all our attempt to contribute towards the knowledge. Some going this way, some going this way, but ultimately they're all aiming towards the same objective. So I hope that this talk that we had in the last 3 days, when I talked to some of you, some of the participants, they said it's too much, it's too technical. Yes, it is. It is supposed to be. It is nonlinear analysis. It is supposed to be. After 7 years or 8 years of us working, I still don't understand it. When my team sometimes come to ask me some question, I scratch my head. What are they talking about? Because every time a new thing comes up, and a new problem comes up that we haven't thought about, a new thing that we have to make a judgment. So it is still a very tedious, complicated process. But it also keeps us on our toes to keep learning, to keep trying to find the solutions and not be content with what other people have written for us and blindly follow. Because all of us are sort of, ready to challenge. Not just for the purpose of challenging, but purpose of understanding, improving, adding to it, and let other people challenge in the next round. So that is the whole purpose of everything that we are doing. And we hope that you can be part of this and you have learned something. Thank you so much.
Thank you very much, Dr. Naveed. On behalf of the ATN organizer, we would like to thank you for your kind participation and hope that we can welcome you to our future event. For those who will join us on the part 3 on handling the practical design issues or workshop with us, we will be meeting with you at AIT campus tomorrow. Any assistance maybe required from your side, please contact our staff. And our certificates are now available for your kind collection outside. Thank you very much once again and hope to meet you again. Thank you very much.